Hello everyone, my name is Dan the Tutor, and today we are continuing our conversation about limits. And actually there's one topic left that we haven't talked about with limits, and that is the limit definition of the derivative. For those of you who don't know what it is, let me explain. Let's say we have f of x is equal to some function that looks like this. X, f of x, and let's say we have the point right here, point 1, x equals 1, okay? And what if I want to find the slope of this line at x equals 1. Just by looking at the graph, we aren't able to tell exactly what the slope is. We can take a guess as to what the slope is, but we're not going to have a definitive answer just yet. What we can do is we can find the slope of linear lines, right? Like from algebra, if we have the slope m is equal to y2 minus y1 over x2 minus x1, we can find the slope of that. And so what I recommend doing then is, what if we just chose 2 points here? I'm going to change this. Let's say we have this point x here, and we have this point x plus h, where this distance here is going to be h. Okay, it's some distance. And then I connected these 2 points with a line, and I can say, hey, this is my slope at this point. Which we all know, that slope isn't exactly correct, right? Like if we were to actually draw the slope, we'd have to draw a tangent line there. So the green here, that green line, that would be our actual slope at that point. And we see the green is not nearly the same slope as the red, but at least then we would have an approximation for what the slope would be, because we have 2 points that we're looking at. And now if we think about what these 2 points are, the bottom point is the point x comma f of x, right? That's the bottom point. The top point is, the x value is x plus h, and the y value would then be f of x plus h, which I know is confusing, but this is like the proper notation, and you don't even need to worry about what x plus h is. It's just saying whatever this value here, that is f of x plus h, and down here that's f of x. That's what it's just the y value at that point. That's what f of x plus h is. And then if we want to find the slope, then the slope would be equal to y2, which is f of x plus h, minus y1, which is f of x, divided by x2, which is x plus h, minus x1, which is just x, okay? And this would be the slope formula for whatever here. And if we had numbers, like if we actually had numbers, like x is 1, h is 2, and then we had the function values in the y-axis, then we could actually find the slope of that red line. And we know this approximation isn't the best because these points are so far apart, right? Why don't I choose a point closer to x, like right there, and then we would have this light blue line here. So now it's actually a better approximation to our green tangent line that I drew earlier, right? Like the blue is much closer to the green. And actually, if you keep thinking with this line of reasoning, we can actually get a really good approximation if we choose a point that's really, really, really close to x. As a matter of fact, if we chose a point that was infinitesimally really close to x, then we could actually have the actual slope of x if we choose a point that is like microscopically close to that x point. And you know what? Since we talked about limits, we now have the proper mathematical language to describe this in words. And that is what we're saying here. We want to find the limit as h approaches 0. If we were to actually plug in h equals 0, what we would get for the slope is m is equal to f of x plus 0, which is just f of x, minus f of x, divided by x plus 0 minus x. And you can kind of see what goes on here. You're going to get 0 in the denominator, and actually 0 in the numerator too. But what's more important is that 0 in the denominator, we can't do it. That's why we can't choose the value h equals 0 when we actually plug in the point. What we can do, however, because remember, limits don't care about what the actual value is. Limits are specifically exist to get rid of those zeros in the denominator by factoring and canceling, or rationalizing and canceling, or any of those strategies we talked about before. And so instead, if we say the limit as h approaches 0, this is what we have. We have the limit as h approaches 0 of f of x plus h minus f of x all over h. This right here is known as the limit definition of the derivative. Limit definition of the derivative. And it's used to find the slope. Used to find slope of any function. We can find the slope of any function if we can compute this limit. Some limits are easier than others, I'll tell you that right now. But let's give an example. Let's just prove that this strategy works, okay? I'm going to prove that this formula works with a very simple example that we can find the slope of right now. And the only slope we can find right now is a linear tangent line, so that's what we're going to do. If I have the function f of x equals x plus 1, right? I know what the slope of this function is because it's already in the form y equals mx plus b. I know my slope is equal to 1 in this example, okay? Now, let's prove that using that limit notation. Limit as h approaches 0 of f of x plus h minus f of x all over h. And now we need to figure out how to plug this in. First of all, don't plug in 0 just yet. Don't plug in 0. You're going to get 0 in the denominator. You're not going to have a fun time. What we need to do is we need to realize two things. One, what's f of x? Well, f of x, we just said it, it's x plus 1. And how about what's f of x plus h? How we would do that is we are replacing every x with now x plus h. And when we do that, we get x plus h plus 1. See what I did there? Whenever we have this notation, f of x plus h or f of x plus whatever, we're just saying replace all the x's with x plus h. And you may be wondering, why are we doing this? Just hear me out, okay? It's pretty cool in the end. Or maybe it's not cool, but whatever, you're still going to do it. So what we get then, if I have this x plus h plus 1 for f of x plus h, let's plug everything in now, okay? We have the limit as h approaches 0 of f of x plus h, which is x plus h plus 1, minus f of x, and f of x was just x plus 1, so minus quantity x plus 1, divided by h. Now before we plug in h, let's simplify here. We get the limit as h approaches 0 of, in the numerator, x plus h plus 1 minus x plus 1 is going to leave us just with h left. We're only left with h. Everything else cancels. In the denominator, we still have h. And we see that the h's actually cancel, and all we're left with is 1. All we're left with is 1. And what does that 1 mean? Why is that significant? Because that just told us what the slope of our line is. The slope of the line, x plus 1, is 1. We did that using, y equals mx plus b first, just by proving that m was 1 in this example of x plus 1. And now we proved it using this complicated limit notation. And why would I ever use that when it's so much easier to just look at y equals mx plus b? Well, you wouldn't in that example because y equals mx plus b is the easiest case. But now let's look at another example. Now let's look at the example f of x equals x squared. And again, if we want to find the slope of that function, what we would do is we would say limit as h approaches 0 of f of x plus h minus f of x over h. Now, f of x is x squared. What's f of x plus h going to be? Remember, we're replacing wherever we see x with x plus h. So x squared now becomes quantity x plus h squared. I'm just replacing all my x's with x plus h. And yes, we do now need to factor this out. So we get x squared, or FOIL it out. X squared plus 2xh plus h squared. We're good. And now we can actually plug in, because we have f of x plus h and f of x. And what we get is limit as h approaches 0 of f of x plus h, which is x squared plus 2xh plus h squared, minus x squared. And then we're going to divide everything by h. So notice the x squareds cancel out, which is nice. And we're left with limit as h approaches 0 of 2xh plus h squared over h. And now we need to ask ourselves, well, we still can't plug in h equals 0 because we're still getting a 0 in the denominator. So how are we going to solve this one? Well, if you go back to our strategies, the 5 ways of evaluating limits, we're going to do method 2, which is factoring and canceling. So how can I factor out the numerator? Well, I think I can pull out an h term here. So we get limit as h approaches 0 of h times the quantity 2x plus h divided by h. The h's are going to cancel, and what we're left with is the limit as h approaches 0 of quantity 2x plus h. And now I'm allowed to plug in h equals 0, right? There's no domain errors. I can just plug in h equals 0, and I get 2x plus 0, which is just 2x. And what does that 2x mean again? That is the slope. And if you're wondering, well, what do you mean a slope of 2x? What's x? That's a good question. Well, x can be any value, right? Like x can be 1, x can be 2, x can be 3, x can be any value, okay? And once you understand what I'm going to say next, slowly your mind is going to be blown away, or at least I'm hoping it'll be blown away, kind of like the realization of like a movie or a detective movie where they're putting all the pieces together, and then I'm hoping that your mind will just explode at some point. So that's my goal over the next minute or two, is to make your mind explode. Here's what it means. Can we think about what the function x squared looks like real quick? It's a parabola, I know. 1, 2, 3, 4. Let's think about what this graph looks like. We know what the parabola looks like, and we know the points too. Because if this is x, and this is f of x, and f of x is equal to x squared, we know the points. We have 1, 1, we have 2, 4, and we have negative 1, 1, negative 2, 4, and from here I can connect the dots. Like this. I need to be careful. Good enough. Okay. Now, what this just said, this function, that slope, we said the slope was equal to 2x, right? So pick a value for x, any value. Well, preferably one between negative 3 and positive 3 here for this example. Let's choose x equals 1. When x equals 1, the slope is 2. Do you see that? Like when I plug in x equals 1 here, we get a slope of 2. And what does that mean? Well, if I look at the slope, like if I were to draw a tangent line at x equals 1, what that's telling me is that the slope of that green line there, the slope is 2. It's not about 2. I didn't eyeball it. I used that equation that we just made to find the slope at that point. Another example, just to prove what's going on here. What if we chose x equals 0? Well, when x equals 0, the slope is 0, right? Like 2 times 0, that's 0. So the slope is 0. Let's prove that. What's the slope of the point at 0? I'm drawing what the slope looks like. And yes, the slope of that line is 0. And one thing you can notice, you can draw any tangent line you want at any of these x values. And we have the slope at all of those points. What's the slope of that line at x equals 2? Well, you plug in 2 times 2, you get 4. And so what you see going on here is that we now have a function, not just a function, but like a way to find the slope of any point on the function f of x equals x squared. And one thing you're going to realize that's super cool about calculus is that we have now just found the path to find the slope of any point of any function. And if that doesn't get you excited, then I don't know what will. Because this is the heart of calculus right here, finding slopes, at first using limits, and then you'll quickly discover that everything that we just did with this limit stuff and the limit definition of derivative, which again is this function right here, that limit definition of derivative. It's important right now for when we only know limits, but it turns out that people have figured out a lot of cool rules and ways to kind of bypass this limit definition of derivative. And there's actually a ton of shortcuts that we can use that will make all the work we just did obsolete. So that's coming next. Stay tuned for that. But for now, just kind of bask in the glory and how beautiful this limit definition of derivative is. It's a ton of work. It's really annoying. I know. I hate it too. But the output, what you can do with it, it really is amazing. And with that, I'm going to let you go. Thank you for joining me. My name is Dan the Tutor. I'll see you next time. Bye-bye.